in this session, we're basically dealing with nomenclature. We're just introducing terms and concepts to kind of give them names, make us be familiar with them, and then in subsequent lectures, I'm going to go ahead and put them into use. So the slides are numbered, except for the title slide. So the number of slides is one less than the actual slide in the series. So I will refer to the slide number that's in the top right of the slides in this presentation. So on slide one, I have to start with a disclaimer, and a big disclaimer, not just because I'm a lawyer and we love disclaimers, but because when you hear thermodynamics, you have many different expectations of what it is that we're going to talk about. So for example, the thermodynamics that a mechanical engineer deals with is looks at different aspects of it than one that a chemical engineer looks at, and they look at different aspects that a chemist, let's say an organic chemist, would look at. Not that the concepts are different, the equations are all the same, the definitions, everything is the same. It's just that the applications are kind of unique to the field that you're in. Certain assumptions that you make, certain information that you look at, you're interested in, those are different. So in this series, I will be talking about the field of chemistry, which is called physical organic chemistry. That's basically physical chemistry that's applied to organic compounds, but the field of physical organic chemistry can really you can be dealing with inorganic, biological, in any type of chemistry. What is it that we do in physical organic chemistry? We are going to look at the thermodynamics of bond making and bond breaking. That's that, and from that thermodynamics, we're going to decide what the reaction mechanism for a reaction is. So my disclaimer is that I understand both thermodynamics in general and chemical thermodynamics in particular are both much bigger fields than we are going to talk about here. And I'm not qualified to talk about the other parts of thermodynamics. I would, if a physical chemist wants to take that up, that would be in their wheelhouse, not mine. So with that in mind, we go to slide number 2. Ask the question of, well, why is it that a synthetic chemist or an organic chemist would need to know thermodynamics? In the very first room in this series, we talked about that chemistry is the science of keeping track of electrons. And putting and determining in which order these electrons move. This one goes first, that one goes second, that one goes third. That is what we call the reaction mechanism, because reactions take place in stepwise fashions, meaning that at every step only one bond is broken or made. If in one step more than one bond is made or broken, that means you're a bad chemist. You didn't set up the reaction correctly, and so you end up with a brown sticky goo instead of a white fluffy solid. So we always just do one bond, one reaction at a time, and so we need to know what the order of these things are. And so by studying thermodynamics, as we will see in the next few lectures, we'll be able to determine the reaction mechanism. So So let's just give a quick example of what I mean by different reaction mechanisms. On slide 4, I have shown an organic compound CXYZL, and L is a leaving group and Nu is a nucleophile. This reaction that I've shown here is a nucleophilic substitution reaction. Because a nucleophile, a few lectures ago we defined what a nucleophile was. A nucleophile is something that has, let's say, excess electrons and is looking for a nucleus to bond with. That is, it has a partial negative charge on it and is attracted to a partial positive charge on another molecule. Here, the carbon will bear the partial positive charge, and the Nu has the excess of electrons. So as we see, Nu has replaced L in this reaction. L, the leaving group, has left, and Nu, the nucleophile, has found its nucleus and has gotten attached to it. Okay, so this is a nucleophilic substitution reaction, but what is the mechanism of this reaction? How does this work? And I here intentionally drew the stick figure of the flat two-dimensional stick figure of the molecule to kind of bring out the re-emphasize the point that just knowing what happens doesn't tell you exactly stepwise what happens. So in the next slide, we have two different possible mechanisms for this. In the first one, which we call an SN1 mechanism, and by the time I'm done with this thermodynamics section, you guys all will know what an SN1 is, what an SN2 is, what the difference between them is, how can you tell all that. So don't worry if you don't know what these things mean at this moment. I'm just going to show you where we're headed, so you know why it is that I'm studying this. So in SN1 reaction, that means it's first order, which means that in the slow step of the reaction, only one molecule is involved. Here, in the slow step of the reaction, the leaving group leaves. And then the nucleophile can attack the central carbon and form the two different CXYZ NUs that we see on top. In an SN2 reaction, the 2 there means is second order. That means in the slow step of the reaction, 2 molecules are involved. So here in the slow step, Nu attacks CXYZL, and we have a transition state which then goes to leaves as in the CXYZ does an inverse umbrella thing. Umbrella in the windstorm thing flips the other way, and Nu attaches to that. So how can we tell the difference between these two reactions? How do we know which one of these is the reaction that forms NuCXYZ? We can do that by determining the rate of the reaction using the principles of thermodynamics we're going to learn here. We're going to do that at different measure the rate at different temperatures, different concentrations, and then we can determine was it a first order reaction or a second order reaction. And this precisely, not CXYZ, but on a more complicated organometallic compound where the metal is rhenium, 75th metal in the periodic table, with a bunch of other stuff around it. I discovered a very interesting question, and so the question was exactly this: was it a first order reaction or second order reaction? And it took me 5 years to figure that out, and that was my PhD thesis. So this is this is a very live question. These types of studies happen all the time. So that was the background for what this series is going to be, and the slide that's up now is our ultimate goal, to be able to understand SN1 and SN2 and their differences. So where do we begin? We begin on slide 5, and for those of you who were at John Malincroft's Bite of Physics a couple of weeks ago, or maybe 3 weeks ago, about springs. If you want to understand this first slide in all its glory detail, I would refer you to John's talk on that, because he goes through the detailed physics of springs that I will not do here. So let's say we have a spring connecting two bodies, A and B. These are two masses, two blocks. And under normal energy conditions, normal means that how we find this spring, right? We haven't added any energy to it. We haven't taken energy out of it. Whatever initial energy was introduced to the system, that is the energy we're dealing with. Under those normal energy conditions, this complex of two bodies and the spring will vibrate. How does it vibrate? A and B will come close to each other. The spring pushes them away. They go away from each other until the spring is stretched to its limit, and then we'll bring the A and B back together again until it's compressed to its limit, and then the whole process just continues. Now, if there's no friction involved, if there's no energy loss of any kind, this thing will go back and forth, will kind of vibrate, or I can't think of the word right now, but anyway, you know what I mean. It'll spring back and forth to the same limit. That is the distance between A and B at their furthest point apart from each other, and at the closest point next to each other will be the same throughout the process. Now I'm going to increase the energy of the system, and I can do that by either like pushing A and B apart from each other with my hands, or bringing them together by pushing them together, or by heating the system. However it is, I'm going to increase the energy of the spring. What happens now is that we'll see the A and B will go further apart from each other than under normal energy conditions. And then when they come back together, they come closer to each other than under normal conditions. So what happens if I keep adding energy to this? That is, if He-Man grabs B and Hulk grabs A and they start pulling, right? That's all. That is introducing energy into the system. What's going to happen at that point is that the spring's going to break, or the system is going to break. Either the spring or the connective point between the spring and A and B, something there is going to break. That's going to separate A and B together. Meaning what? Meaning that the external pressure, external energy was a lot greater than the internal energy keeping these things together. In point 2, the internal energy still dominates, and that's why the spring doesn't break apart. But in 3, the external energy dominates, and so the spring breaks. I think this is pretty, I hope this is pretty intuitive for everyone. So how do we represent this on a graph? That's on slide 6. These are, you should look at these as two different graphs. That doesn't mean that in B the distance between the blocks is greater. It's just that the same graph, but I put it over there. So under normal energy, the ball, this is a ball in a valley, it goes up on one side and then comes back down. So it goes up on one side means that the distance between, let's say it goes to the right. The distance between the blocks increases until it gets to the top of the red arrow, and then that's as much energy as it has. Then it comes back down to the middle point. That's where the distance is at equilibrium, and then goes back up the other way. That's when the two blocks are getting closer to each other until again the energy gets to the top of the arrow and then comes back, and does this over and over again. If I add more and more energy to it, we'll see that it goes further up the sides of this valley. Again, this should be intuitive for everyone. This we have seen this in real life with balls and valleys and etc. Especially if you've like played skee ball, you've seen this. So we go to slide 7. So what happens if on the right-hand side I keep going, right? Instead of stopping at the top of the arrow, I keep going. I keep increasing the energy, or I keep increasing the distance between the two blocks. I apologize for the crudeness of my graphs. I really don't know how to do graphs in PowerPoint, so please chalk that up to my age. So the graph for spring breaking looks like this, that on the left-hand side, position 1, spring has a certain energy. That's the normal energy we were talking about. And so it's right there. The energy doesn't change. But then we're going to increase the energy or increase the distance. We're going to go up the black graph towards the peak. At the peak, that's the highest energy point. At that point, the spring breaks, because at that point you see that going to the right, meaning increasing the distance between the blocks, and going to the left, decreasing the distance between the blocks, that is going to be energetically equivalent. So half the time it goes one way, half the time it goes the other. But in this case, we're continuing increasing the distance, so spring breaks. Spring breaks, when the spring breaks, energy is lost. How's energy lost? Well, the spring contracts, and so that some of the energy in the spring is now converted to mechanical energy of the spring moving. Spring hits the block, makes a noise, causes vibration of the block, vibration of the spring itself, vibration of the air around it. All of that is dissipation of energy. So energy is lost until energy is no longer lost, and we end up with a new resting position. And that resting position, in this case, we say that the system has more energy than it started with. Let's say why? Let's say it's because the two blocks that are on the frictionless surface continue moving. So they have a whole bunch more kinetic energy than the initial spring had, and so they're at a higher energy level.
Or they are heated maybe because of the friction.
Yes,
they have higher
absolutely.
temperature.
Yeah, a whole host of reasons would. That was just one example, right? So if we go to slide 8. I've shown here that it could be two ways, right? That is, the two separated blocks could have more energy than what we started with. That's the graph on the left, situation I. Or it can have less energy than the spring initially. So So how can it have less energy? Well, it's not a frictionless surface, right? So it loses energy to the surface. The internal energy losses that we talked about due to vibrations, heat, noise, whatever, this and that, might be greater than what the internal energy initially was. So we can have both of those. So on the left-hand side, we have A plus energy equals B. That is, in order for us to go from A to B, we're going to end up with a net negative energy. We have to net put energy into the system to go from A to B. And that energy was the muscle energy that we used, that was greater than the dissipation energy. And number two, we have A is the same as B plus energy. That is, it gives off energy. So the net effect of situation two is that we have introduced energy into the environment from the system. So that could be heat that gets transferred to the surface because of friction. It could be the noise and the vibrations, any of those. But what happens is that the total amount of energy loss, total amount of energy of the system shows energy loss to the environment. So if we put both of these together, we're going to see what's in the middle, that A plus energy equals C, and C equals B plus energy. So if I'm at C, either way I go, I release energy. Or if I'm at A and B, no matter which direction I want to go towards C, I have to introduce energy into the system. So C is an energy hump. It's not a valley. All right. Let's do chemistry now, right? This was all blocks and springs and things like that. Let's go to slide number 9. The molecule is HCl. Here, H, we're analogizing now. H, oh, sorry, this. So H and Cl are the blocks A and B, and the bond between them is the spring. So the bond has a certain amount of energy, right? It is vibrating at a certain frequency, so it has a certain amount of internal energy. I'm going to separate out hydrogen from chloride because I'm trying to break the HCl bond. This is a heterolytic cleavage, meaning that Cl is going to end up with all the electrons in the bond, and H is going to end up with none of the electrons in the bond. So as I pull them apart, what happens is that it becomes more and more difficult for me to pull them apart, because that delta minus that's forming on chloride and that delta plus, that partial negative charge on chloride and the partial positive charge on hydrogen, those are attracting each other. And they're attracting each other more and more. And so it takes a lot more energy. But then it gets to a point that it is going to be energetically favorable for the electrons to just leave this bond and go to Cl and form Cl minus and H plus. So I start with HCl. I go through my hump, which is the highest point of energy as I'm pulling these two apart, and then I end up at the bottom right which is H plus and Cl minus. Let's give names to these things. So first of all, this graph that's here, uh, uh, you will see this again and again and again and again and again. This graph, this type of graph defines chemical thermodynamics. And so we are all basically in chemistry, when we do thermodynamics, trying to figure out what the enthalpy is, what the entropy is, things like that. We're drawing this graph. So let's figure out what the components are. The y-axis, the vertical axis, is energy. It's G, that's the variable which defines the Gibbs free energy, and it's in the units of kilojoule per mole. The D, horizontal or x-axis, is the distance between the atoms. It doesn't really have a letter designator, but it's in the units of angstroms. Now that angstroms really we don't care about. It's not really that important for the purposes of, as I said, physical organic chemistry. It's not important where C is in respect to the distance between the atoms. It's more important where C is energetically. Where is it up or down on the vertical axis? A are the reactants, B are the products, and C, this is a new term, C is the transition state. We'll hear transition states again all the time. So let's say if I go to slide 4 again, on the SN2, the middle structure is the structure of the transition state. And you will see it has the brackets, and the bracket says double dagger. Every time you see that double dagger sign, we're dealing with a transition state. So that's a transition state in SN2, whereas the top one in SN1, the molecule in the brackets, that's an intermediate. So what's the difference between an intermediate and a transition state? Transition state doesn't exist. It's not a molecular entity. It's transitory. And so you don't see the transition state in spectroscopy or by any means. It's a theoretical structure, whereas an intermediate, it has existence. You see it in the flask using spectroscopy or whatever. So that's a difference between intermediate and transition states. So if I go back to 12, slide 10, excuse me, slide 10, that C is a transition state because it's a hump. If it were an intermediate, it would be a dip there, right? Because I would now have a molecular entity that has existence, and it has an energy minimum at that location. So transition states are, as I said, theoretical, transitory, based on our models of chemistry. Slide 11, I'm going to show you what are these are the two most important things we talk about in thermochemistry. So G, the Gibbs free energy, is impossible to calculate, because we're going to see later, you need to know the internal energy of the molecule. And there's no way for you to be able to calculate the internal energy of the molecule, because we can't account for all the variables, all the things that go into uh, uh, energy of a molecule, account for all of those and calculate what the absolute value of the free energy, Gibbs free energy of this molecule is. Instead, what we can do is figure out in the process that we're studying, in the reaction that we're studying, what is the change in the Gibbs free energy. That we can easily measure experimentally and calculate and all that. So what is important to a chemist is not G, but actually delta G. So the bottom bar that says delta G, that shows the difference in free energy between the products and the reactants. So that is as much energy as, in this case, given out to the surroundings when this reaction takes place. Delta G double dagger, and we said double dagger, every time we see double dagger, that deals with the transition state. That is the free energy change for us to reach the transition state. So because we need to have at least delta G double dagger energy in that system for the reaction to go forward, that is called an activation energy. That is you need to have that much energy to activate the reaction to go forward, or we call it the activation barrier, because it is an energy barrier for the reaction to move forward. So how does this work, right? I'm sitting there on the couch, eating chips, drinking beer, watching football. My friends say, hey, we're all going to the sports bar to eat nachos and watch the game. Come with us. And I think and I say, oh my God, that is going to be so much fun going with all the guys to do this. So that's B, right? It is where I want to go. However, I can't get off this couch, right? And so I'm just so tired. I shoveled snow all day. I repainted the whole house. I'm just so damn tired. I can't move. So no matter how much fun it's going to be with my friends, I just don't have the energy to get off that couch and go out with them. That's the activation barrier, right? That the outcome may be something that I really, really like and will enjoy a lot, but I just don't have enough energy to go ahead and do this. So this reaction, as I've depicted it here on slide 11, that's that kind of reaction, in that they're sitting there, we're telling them, hey, come to B, and they look around and they say, all right, there's enough energy in this solution for me to make it over, get off the couch, make it over C and go to B. Or no, it's too cold. I don't have enough energy. It's and so we can't go. So I'm going to move on to slide 12. So this is Gibbs free energy. We talked about G, and so G is calculated as H minus Ts. Yeah, that means the free energy is equal to enthalpy minus the product of temperature and entropy. And this is why we can't really calculate G, because we don't know what enthalpy is in the whole system. We don't know what entropy is in the whole system, and there's no way for us to figure that out. So instead, we go to the bottom equation. Delta G equals delta H minus T delta S. So when we talk about delta now, we're extremely specific, right? because we're talking about a change that happens in a very specific reaction. So we say free energy, the free energy the free energy of the reaction. So that's delta G. It's not the free energy of the molecules, it's the free energy of the reaction. And the free energy of the reaction is the difference in the free energy of the molecules. So when we say delta G, we don't say the change in free energy. We just say free energy of the reaction is equal to the change in the enthalpy between the product and the reactants minus the product of the temperature of the reaction and change in the entropy between the products and the reactants. So this was the last slide. I just want to ask a question to kind of again bring this home. How do you melt ice? There are two ways we can melt ice, right? You can wait until spring thaw when it gets warm and ice melts, or you can sprinkle ice on your sidewalk. Salt on your driveway and sidewalk, and ice will melt. So here, I live in Salt Lake City. We all have buckets of sidewalk salt, and we periodically salt the driveway and the sidewalk, so nobody falls and breaks their legs and sues us. So why do those things melt the ice? For ice to melt, it means that delta G of melting has to be negative. If delta G is positive, the reaction won't go forward. If delta G is negative, the reaction will go forward. The fact that the ice is not melting means that under the conditions that we're at, the delta G of melting is positive. So I have to make it negative. How do I make it negative? I look at my equation. Delta H. Can I change delta H? No. That is bond energy, all of that. You don't have any control over that. It is what it is.
Doesn't it have to do with the pressure as well?
Not, that's in gaseous systems. In non-gaseous systems, the effect of pressure at atmosphere pressures is negligible. So yes, I can melt ice by putting it under 2,000 atmospheres, and then it'll melt. But I'm talking about on a normal everyday life situations. So I can't change delta H. So how can I make delta G more negative? I can make the T delta S term more negative. How do I make the T delta S term more negative? I raise the temperature. I raise the temperature, minus T delta S becomes a lot more negative. Delta G becomes negative. Ice melts. Or I add salt to it. What is salt? Salt introduces randomness into the system. What is entropy? Entropy is a measure of randomness into the system. So if I add salt to it, I have increased the delta S of the system. That increases the value of the minus T delta S term. Delta G becomes more negative. Ice melts. That is a mathematical way of discussing this aspect of thermochemistry. There are non-mathematical ways of describing this about what happens to the molecules and atoms and bonds, but that is for another lecture. So I'm done with today's talk. The last slide is what it is we're going to talk about next week. I've talked about enthalpy and entropy without telling you exactly what they are. I gave you just very brief definitions. We're going to go deeper into those two terms to really see what is a chemist's understanding of enthalpy and entropy, as synthetic chemists, because a physical chemist would have the same understanding as a chemical engineer would, which is not the same understanding that I have. Then we talk about, okay, we introduce delta G double dagger and delta G. So what? What can we? What information can we glean from those? Why should we care about them? How does that affect us? And then, if we have time, I'll get to reaction rates and rate determining steps. Well, I'm done, and the floor's open for anybody who wants to come up, ask questions. Just raise your hand, and let's hear from you.
Well, thank you, Sam. Wonderful as always. Let me ask you about the name. This is like the 100th time that people try to explain to me what free energy is, and I always wonder what's the difference between the free energy of a molecule and the energy, just the energy. Because like for the most of your talk, you've been saying, oh, this has this energy of bond, and then when the bond breaks, there's this energy released, etc., etc. So why do we say free energy to distinguish it from the relativistic mass energy? Is this the point? Sorry, Sam, you're muted, I think.
Sorry, I didn't realize that. So, yeah, so energy in thermodynamics can refer to either enthalpy or Gibbs free energy. Because both of them are energies and both of them are in units of kilojoules per mole. So, in order to distinguish between energy of a bond and free energy, which is the energy of the system itself, we I don't know why we say free energy. That I don't know, but I know we call one free energy, the other one just energy, to distinguish between enthalpy and Gibbs. So it's a very good question. I actually I'm ashamed to say I don't know the answer.
We'll wait for next week when we do enthalpy, then it'll be clear.
Hi, Richard.
Yes, I thank you for your. This is eloquent and very articulate. I like the slideshow
Oh,
to
thank
work
you.
along with. Thank you very much. I did put two notations in the chat. One thing, I have family who are in the airlines industry. An uncle that was a pilot. One thing about the temperature of water when it's in the northern climes, when there's a plane flying, they very often have to spray the plane to de-ice it and remove the ice from the wings when it's accumulating on the wings because it's dangerous. And in point of fact, not really ice, but cold caused one of the NASA disasters in the 1980s. There was an O-ring that got so cold that it did not function properly. It actually changed the chemical compound of I believe, the O-ring that was holding in around the spaceship. I forget which one was flying. It actually was the lethal one that killed several of them. If anyone can remember which.
It was Challenger in
Challenger, yes.
1986. Yeah.
And Richard Feynman is the physicist Richard Feynman proposed, and it turned out to be, in the long term analysis, that was the temperature of the O ring around it to hold in the gases inside the chamber failed, and it caused ultimately it was determined that that is what caused the failure. So temperature and activity in our civilization and the status of water is very important. I just want to thank you for your your discussion today.
Thanks a lot. Yeah, the solution that they spray on airplane wings is not a salt solution because that would be somewhat dangerous for two reasons. Number one, the temperature that the airplane flies at cruising altitude is about -50 to -60 Fahrenheit. And that's below the freezing point of water salt. So it doesn't take the freezing point low enough, and so you still are going to get a chance of freezing. The other thing is that when the water evaporates, you end up with this crystalline solid, which can get into the mechanism of the flaps and ailerons and things like that, and cause damage. So that solution is something similar to ethylene glycol, which is in your antifreeze, but so chemically is similar to that, but it's a little bit more complicated, so that it kind of brings the freezing temperature of water well below -70, -80 Fahrenheit. But the principle is exactly the same that I said here. It's exactly that delta G equals delta H minus T delta. So you're doing the exact same things with that alcohol solution as you would do with salt.
Thank you for the clarification.
So sorry, I don't get a chance to read the chat. If you have a question in the chat and you want to ask it, please come up and we can deal with it. If there are no questions, we can say our goodbyes. What do you think, Shamash?
Yeah, I'm waiting for next week, actually. I can't
Right?
wait now. This makes so much more sense as I hear you and John explain it, unlike my high school professors. So let's do that.
Oh my God, learning this in... Okay. I went through college. I got a bachelor's degree in chemistry, and I almost had a bachelor's degree in philosophy. The only reason I didn't have that was because I didn't want to take a year of
Because you
Greek
were
or
trying to be
Latin.
clever. That's the reason. You were doing
No,
the
no,
right
no, no.
choice.
I just didn't want to take a year of Greek or Latin that was required for a philosophy major, so I ended up with a minor.
Shame, shame,
I
shame,
got a
shame.
PhD in chemistry. I went to law school. The most difficult class I have ever taken, the one that made absolutely no sense whatsoever, was freshman chemistry in college. It was absolutely the worst class. But then I took organic chemistry. And I fell in love, and that's when I became a chemist. So I don't know why they make people take freshman chemistry the way it is taught now. I mean, I do know, but it's a long discussion. So
That's funny because that's the only chemistry class I ever took.
that's the only chemistry class that anybody who's
Chem,
not a chem
Chem
major
201.
takes. Right? I mean, unless you're a chem major or you're bio. I mean, bio majors would take OChem also.
Pre-meds as well, some of it.
Yeah, pre-meds would have to take OChem. But then everybody else only takes freshman chemistry, and it's the most useless class in all of college. It doesn't teach you anything that you can use in real life. It doesn't teach you anything. It's like you go, junior year, you're taking advanced PChem, and you're like, oh, so this is what they were trying to teach us 3 years ago in freshman chem. So why didn't they say that?
I enjoyed the lab stuff, but the class itself, I felt like it seemed like accounting. And now that you say this, I feel like I have a very unfair view of chemistry that I need to revise. Because yeah, that's just all I ever took.
Yeah,
Well,
I
it
agree.
it feels like accounting because it is accounting, right? I mean, the thing is, all you're doing is calculating the pKa of this acid, calculating the KEQ of this reaction. What is PV equals nRT? Da, 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 da. And then you're like, really? Do chemists do these things? No, we don't do these things. We do chemistry. Hi, Kevin. Welcome to the stage.
Oh, hi. How you doing? I
Good. How are
heard a
you?
lot. Oh, pretty good. Yeah, I heard a lot of this. Yeah, I went back to school for bioengineering, so I'm sort of you know, refreshing, my knowledge for all this. So this is great. Thanks a lot.
You're welcome.
I'm trying to think of some questions that, like, tell me if this gets too much in the weeds, but like, what about concepts of like hybridization and like its significance in determining the shape and reactivity of organic molecules? Is one question I thought of.
Yeah, we have talked about those in our previous rooms in this series. So if you go to Scientific Discourse, you can find the recordings of previous rooms, and we talked about hybridization. I don't know, in the fourth or fifth. This is the 16th room in the series, and so I kind of paused in the middle of not middle. I mean, I kind of finished the reactions of some of the more important biologically related functional groups in organic chemistry. We briefly touched on that, and then I'm kind of taking a little tangent in thermodynamics now because if I'm going to go back to continue that discussion, we need to know, SN1, SN2, rate determining step, things like that. So I thought we'd take this little break before we continue with that.
Oh, okay. Well, okay. Yeah. More specifically for Gibbs free energy, what about like predicting the spontaneity of organic reactions? Like how does it differ from, you know, enthalpy and entropy, in this context, I guess.
Yeah. So that's a little bit ahead of schedule. So we'll get to that in the future sessions, but as I kind of briefly mentioned that if delta G is negative, the reaction moves forward, but if it's positive, it doesn't. So if it moves forward, then that's spontaneous. But then we need to kind of, for spontaneity, we need to go back and discuss reactions that are under kinetic control or thermodynamic control, and what is it that we form spontaneously. So all of that are going to be in the future rooms. This was just the first introductory room that really all I wanted to do is introduce the graph of free energy and tell you guys what the components are and why all of that. So really, slide 12 uh, is the aim of this room. If you understand slide 12 and you don't understand anything past that, then you're basically with us.
Oh, okay. Yeah, yeah. Yeah. Let me look at that before I try to ask
Yeah,
you. Okay, I'll look. Thank you.
sure.
Can I go back to your example about how water melts with ice,
Uh huh.
or how Shit. How
Ice
how ice
melts
melts with
with
salt.
salt.
So
Yes.
does it work if you spray sugar or sand or more ice on it, or does it have to be salt because it melts quicker? Like the ice absorbs it, and that's how it introduces more entropy to it.
They all work. The good thing about salt is that uh, you get 2 moles of disruptants per 1 mole of molecule. So if I throw sugar, I just get 1 mole of disruptant. But because sodium dissociates into sodium and chloride, it's as if I have sprayed twice as much on the thing. The other thing
Oh.
is uh, salt, both sodium and chloride have the highest solubility, have very, very, let's say NaCl has the highest solubility of common molecules. Common meaning that if I walk into my grocery store, I can buy it. Okay, so sodium chloride has the highest solubility of that, and is really cheap. So salt is a lot cheaper than sugar. The other thing is that if I spray sugar on the street, the runoff is going to create havoc environmentally, right? All the lakes, all the algae bloom, all the, it's going to be crazy. Whereas added salt goes into the ocean, so it doesn't do anything. So because of all that stuff, that's why we use salt instead of other things. But we really could use anything. So in fact, why is Fahrenheit the way Fahrenheit is? Right, 32 is ice freezing, 212 water boiling, and all that. It's because Fahrenheit made the coldest thing that could make a slushy, and that was a mixture of ice in the dead of winter with copper sulfate. And so really, really cold, thick ice, if you add copper sulfate to it, it melts it, and the melting is 32 degrees of Fahrenheit below the freezing point of regular ice. So Fahrenheit made that his zero, the coldest temperature he could get to, and then he marked his thermometer. He determined zero. He marked the the degrees, and then he went around and measured things. Whereas Celsius limited both ends. Celsius measured it in boiling water and in ice water. Fahrenheit only limited it to the ice and copper sulfate. And that's why ice melts at 32, water boils at 212, our body temperature is 98.7, right? We get all these weird things because instead of just like a normal person figure out what the outer limit is, he just did it that way. So the point of that rant was copper sulfate also gives you that. But you don't want to spray copper sulfate on your street because then your whole city becomes blue, and then excess copper is going to damage marine life. So
We don't need more blue in winter. That's not what we need.
no, yeah.
I may have some questions that correlate to this possibly. Like, uh, how does your how does can you discuss like how like entropy and enthalpy contribute to the Gibbs free energy changes you've observed?
I briefly mentioned that in slide 13, where I have the equation for Gibbs free energy that gives the relationship between enthalpy, entropy, temperature, and Gibbs free energy. A more detailed conversation is going to be next time when I go ahead and I in slide 14 I have put up the topics for next time. So that's when I'm going to exactly talk about enthalpy, what is entropy, how do they contribute to delta G, and then what do we gain from delta G and delta G double dagger, things like that.
Oh, okay. Yeah, I got it. Yeah, I'm at quantum photonics. Yeah, I have to look at your other 15 discussions. Yeah, thanks a lot. I'm getting too far ahead. Thank you.
Sure. Yeah. All right. So if there are no more questions, Shamash, why don't you tell us about your upcoming room?
Sure. As you guys know, we're running 3 weekly rooms in the scientific discourse. There's this one on Monday. There's another one on Wednesday, so that's 2 days from now, at 17:30 GMT. It's about philosophy usually. We talk about more philosophical issues that have to do with science, logic, mathematics, all that sort. We've been looking on the philosophy of science and its evolution since the beginning of the 20th century. So we did 2 rooms about logical positivism. And moving forward, we want to discuss issues like demarcation issue, what is science, what is not science, how do we know, etc. The room on Wednesday will be about another possible, let's say, solution for or philosophy or option that emerged in the beginning of the 20th century, which is operationalism by the physicist Percy Bridgman. So we're going to discuss that. We're going to see how it helps. It's a very good idea. It's better than the logical positivist idea if you've attended the rooms. I'm going to post a link in the chat a few moments from now. You can log in the event, put it on your calendar, and hope to see you on Wednesday. Also, John Mallinckrodt's room on Friday. I don't know what it's about, but he runs amazing rooms about physics as well. So if you enjoyed Sam's room, you most likely will enjoy John's room, also 17:30 GMT. Thank you, Sam. Wonderful.
Thank you, guys. Thank you all for being here and supporting our rooms. And please, next time, come up, join the chat. We like to hear from you guys. So I look forward to seeing you in Shamash and John's rooms in the coming days and also right here next week. Thank you very much. I'm going to leave you with I Can't Go On Without You by